How much atomic does a sand meet? There is almost an invisible sand at the end of your finger. From the outside stands as insignificant, part of a simple substance. But when we examine closely, we encounter numbers that push our mind. Here our question is quite simple. How much atomic inside this tiny silica crystal? Can you guess? How many atoms are found in one sand? When you guess, let's take a look at the atoms that make the structure of the sand. A typical sand is mainly composed of silicon dioxide, namely silica crystals. A large part of the weight of these particles consists of silicon and oxygen atoms. To calculate the number of these atoms, we use the average volume of sand grain, about 0.1 amib3, the density of silica, and the mass of molars of atoms. When we take into account the density of silica and the mass of atoms, a rather surprising table comes from us. What is your mean time? How many atoms are in one sand? Maybe you have a few billions, perhaps a few trillions. But the fact is much greater, because there are about 10 to 20 catamaran atoms in one sand. Yes, there are 16 atoms above 1016 to 2x10, and if you try to count each atom in this sand, it took full 317 billion years. So an ordinary sand in appearance is the universe of a crowd, which we will not see in fact. Each of its cores, electron cloud and atomics standing side by billions of years history. This information is a mathematical reality. There are 20 catabollions atoms in one sand, but our mind is difficult to detect it not. It is really difficult to accept that one sand consists of small particles with catabollions. You must, because the main thing lies how small the atom is. Atomic is incredibly small as it will lower our daily perceptions. It is almost impossible to imagine the smallness. Take a hair wire to your hand. See nearby. It is impossible to see a width, but you can notice when you are approaching too. The average thickness of a human hair wire is about 0.05 mm, that is 50 micrometer. The diameter of a single carbon atom is about 0.2 nanometer. When we calculate with this data, it is possible to knee about 500,000 carbon atoms across the width of a hair wire. Let's grow our scale to better understand this dimensional difference. For example, you host atoms with trillions in your chew. If each of these atoms had a mucus size, then your hand suddenly reached the volume of the entire world. Here you can find atoms in the sand grain thanks to this incredible little. In one sand, we saw that the atom can fit. This count is big enough to push our mind. But the main surprising, this is what the huge crowd really resembles, because each of these atoms is not like a filled sphere. On the contrary, it is largely composed of space. So what fills the sand grain is an extraordinary layout of repeated cavities for countless times. This is one of the largest paradoxes on the essence of the substance. While a sand feels solid enough to hurt our finger, a large part of the small atoms that make it is actually all about it. This space is the only reason why sand is solid. Now it's not easy to imagine this gap. If we turned the atom into a huge stadium size, the core would just be a tiny misket that stands in the middle. The electrons would be far away from a few dust grains, circulating in the outer tribunals of the stadium, and everything remaining back would be almost completely spaced in the combination. Approximately 99% of the atomic volume consists of pure nonus. That's a solid sand that we've kept, in fact. It's composed of these tremendous spaces that were in-house. We will continue our questions. If these atoms consist of almost completely space, how do they stay in one way? The secret that the atoms remain in one way is hidden in nature laws. Protons on the core are positively installed. The electrons are negative. The Z loads attract each other. In this way, electrons do not break from the core and do not fall into the draw. They are kept in certain energy levels. Other atoms approach each other. Electron clouds work on overlapping. However, a basic rule known as the principle of Pauli exclusion does not allow it. Two electrons cannot be found at the same time. Thanks to this prohibition, atomics cannot be imported. Our questions have not been over yet, but while the atoms approach each other, the electron clouds are blocked for each other. They push one. So I didn't need to disperse these atoms. So if there were only thrust force, atoms were away from each other, and the sand is scattered from the very. Here the shot force is activated. Each atom has positively installed protons in its core. As we mentioned earlier, these protons apply not only to their electrons, but also strong shooting to electron clouds filled with negative load of neighboring atoms. So the atoms are both pushed and pulls at the same time, so they do not get closer or distracted until atoms are fully stuck. Instead, They remain at a point where shooting and push forces are balanced. Here we give the chemical bond name. Silicon and oxygen atoms create a three-dimensional network by combining regularly through these bonds. This structure is in a highly robust form, namely quartz crystal. Atoms are not allowed in these cages. They are only trembling, but they are never integral. As a result, the sand we hold is actually a structure that consists of atoms filled with spaces. But invisible forces, which are effective in these cavities, turn it into a hard, durable, and difficult solid. So, the gaps that do not appear inside the sand, and forces that hold it together, showed us the essence of the substance. Now let's expand our perspective a little. So far we learned how to fit the atom into one sand. But let's deepen this discovery. Let's put all the sand grains in the world with stars in the universe. The classic question, is the sand grains in the world more or stars in the universe? The stars we see on the sky are actually only owned by the Milky Way galaxy. Yet there are about 200 billion galaxies like this in observable universe, and there are 100 billion stars in each. The number we have reached when we do this colleague is about 10 more than 22 stars. That's a huge size that appears when you put 22 0 to 1. Another calculation method takes into account the volume and star density of the universe, which gives a similar result. Two different ways reveal the same tremendous size. Now let's turn our eyes into the world again. The total length of the beaches is about 356,000 km. One of these three is sandy. The average beach is 50 meters wide and 10 meters deep. The total volume is about 610 ma3. When we divide this volume to sand grains with an average of 0, the number obtained varies from 10 to 20 to 10 more than 22. So sand grains in all beaches are similar to the number of stars in the rough universe. But the table is still clear. The stars of the universe are usually a few steps ahead, even according to the best estimates. There are about 10,000 stars in the sky for each sand in the world. Are I going to say something more crazy? In fact, there are more atoms in sand grains around the world. So there is a balanced status that pushes our imagination here. This tiny sand that fits the tip of our anodyne finger is atomic in the cations. On the other side, there are stars that leave all the beaches of our planet when we get to say in the universe. Two of them express the same truth. The universe is without flying until it exceeds the limits of our mind in both the smallest scales and the largest scales.